we go. We were talking about estimating things. We know how to make hypothesis tests and see like get like yes or no answers with p-values and things now. But we were learning to be a little bit more wary about our results. So we're able to estimate the values of things given our samples because usually we've got like something we care about. We would like the median of our of the population. We would like the average age or something, median age, median salary, and we get like a little tiny sample and we ask some people questions and we get answers from them, and hopefully it was a nice random sample. If it was, you can make some good conclusions from it. But once you have your sample, right, you're gonna do the median of that or the average of that. You're gonna calculate what you cared about for the population from the sample, and you're gonna try to infer things about the population. And the age-old question is, well, the sample that I took was just one sample out of many that I could have taken. I could have asked different people and I would have gotten a different result, and the median value for the salary or the average age would have been completely different. So, like, I can't really claim that the average that I got from the sample or the median that I got from the sample or whatever I try to calculate for my statistic, I can't really claim that that is the right one for the population. So the goal is to maybe can I use that sample's data still to get maybe a good range where I'm pretty confident that the value lies. And that's where we were going. So we wanted a confidence interval. That's where we stopped. We would like to be able to say, like, I can calculate a range of values for this average age, and I'm 90% confident that the true value is within that. That's something we're able to do thanks to this concept called bootstrapping. So bootstrapping was the idea of we took our one good sample. It resembles the population pretty well because it was a random sample in theory. If we resample from that, we take just as many things, but we sample with replacement this time. Maybe we double count some people, don't count some other people. That is still going to look like the population, but in a different way, and will help us see how things could vary. All right, those resamples they'll be different, but yet slightly similar. And in theory, that's as if we took another random sample from our population. And so we'll get a bunch of different values because they're different samples at that point. Our resamples are different samples. We'll get a bunch of different values for our statistic, and we can use those to see how often we got a certain range of things, and that gives us our confidence intervals. Okay, so that's where we stopped. And we are going to continue slightly more before I ask you to try things. I mean, we'll follow along together, I think. But I want to show you this last bullet as well. Like, first of all, you can control the percentage by being like, you take the middle 90%, that's your 90% confidence interval. You take the middle 95%, that's a 95% confidence interval. So you start from like the 2.5 percentile value all the way to the 97.5 percentile value. That gives you a 95% confidence interval. But you always got to stay towards the middle because that's where the good stuff is. So yeah, I want to try this all over again. Last time, what do we do it with? We did it with the salaries, right? The salaries for the San Francisco employees. We pretended we didn't actually have all of their salaries, and we saw how good a bootstrap would do to predict a range of median salary values. That was fun. I guess towards the end we also did some stuff for the average, and that's cool too. But yeah, let's talk about just like confidence intervals in general. That's where we're going today. That's what we'll practice with, because that's kind of the culmination of all this stuff. So I am going to work with the that data set that we were using in the last chapter about women who smoked during pregnancy. So let's read that one in. Table.read table. It was called baby.csv. So I'll call that, we got some births. And so here's that table if you remember it. You've got all these different factors. You got the weight of the baby, how long was the gestation, how old was the mother, how tall was the mother in inches, how heavy was the mother, how much did the mother weigh in, I guess, pounds, I assume, and then whether or not, false or true, did that woman smoke during pregnancy. So yeah, we have all those things, and I would like to do a confidence interval here, because this is kind of what you would really get in real life. This is a bunch of mothers from, I believe, one hospital, and that is not a population this time. We don't have the population this time. We have no population data this time, just a sample. This is a sample of mothers who came in and had a child. We don't have every mother who's ever going to come to this hospital in the year or whatever. We have a few, okay? A few that they took data on. And so we'd like to infer things about the kind of women who go to this hospital, or the women who, like, I guess, go and have a baby at this hospital in the time period that they took this data. Because that's the whole point, that this was a random sample. We can conclude things about similar people in this population, okay? That's what we're doing. So let's work with age. I think age is a good one that your book talks about a little bit. So let's look at just the age. Births dot, you can do a histogram on the age, maternal age. Whee! Beautiful. So there's that one. We have it. And it looks like the women at this hospital, I forget when the time period was when this happened was, but it looks like they're, I mean, it's a little skewed left there, or maybe skewed right. I forget the direction. We'll deal with that later. But it looks like the 24 to 27 range was about the most popular one there. So let's do the average. What was the average maternal age for the women in our data set for this sample? How old were they when they had their child? So mp.average, births.column, maternal age. Oops. It looks like they're, yeah, just a little over 27. And I guess this is kind of, the data doesn't have like, oh, they're 27 and a half or something. So like you do have to take this with a grain of salt. But like if you just take their age, it looks like on average it's a bit over 27. So that's that one. And so the question is, this is a sample, right? This is a sample. How old, like what's a good range of ages? Because like this is just one sample of women having children. What if we took a different one? What would have been their average age? So like, what we would like to determine is the true average age of the population of mothers having children in this hospital. Does that make sense, that question? That's what we'd like to know. And this is just one value for our particular sample. We can use bootstrapping to get a confidence interval, give us a range of age values, average age values, to see like, we're 90% confident that it's within this amount. Okay, so I would like you guys to try a little bit of this. We'll just do a bunch of trial and error today, but I think this is a good place to consider what we did last time. So please go to the code from class from last time and get all this stuff. Go and read the table and look what we were doing, because what we'd like to do here is exactly the same as this one. We'd like to do a bootstrap sample. We'd like to resample from our population and take a resample and compute the average age of that resample. That's us getting a new pretend sample from our population. And if we took a good random sample the very first time of these mothers, then the resample will be another like similar kind of sample that's yet a little bit different and lets us conclude things. So we want a one bootstrap, I guess, average or mean. We did this for the one again, so you kind of want to stare at this one, right? So your crushed ice right now is write a function that resamples from the population. You can do it shorter like this. You can just be like your sample, births dot sample, instead of births dot samples, births dot num rows with replacement equals true, because those are all the defaults anyway. You could have just said dot sample with nothing. So I think this is the one you want to stare at. Try to make this function, one bootstrap average, one bootstrap mean, whatever you want to call it, but take a bootstrap sample of our births table, please, with the same amount with replacement, and then give back the value we're trying to find again, which is the average maternal age. Does that question make sense? That idea makes sense? That's what I'd like you to try right now, please. We'll just keep on doing that today. So, crushed ice. Try to create a function that gets a resample that resamples from our data set from our original sample using the bootstrap method that we know and love now, and give back the average age of the mothers in that new bootstrapped sample. I guess that's a verb. All right, so try to make a function and call it one bootstrap average like we did before, one bootstrap mean maybe, and try to call it, and notice that the average value that you're going to get back is going to be slightly different. It's going to hover around that because that was the original data set's average. But because you're sampling with replacement this time, you're going to get different values, and that's going to tell us more about the population. If you have any questions as you're trying out, maybe a couple minutes. Yeah, try calling it a few times, make sure it's different, right? It's the random sample should give you different things. That's a good way to check if you're doing it with replacement or without replacement. If you take all the same ones without replacement, you're just getting them back to you in the same order. Oh, sorry, in a different order. Good question.
If this one sample if that's nothing this one like sample.
Yeah, if you were to print out that right now, it would be just a bunch of rows. It would look like the table again.
Okay.
And it would have all the same columns. You carried about one special column, just the age column.
Oh, okay.
So essentially, you're gonna run this line
over again,
but with your receipt.
Mm-hmm.
Yeah. All right, I think that was a decent head start. Are there any questions as we were trying? Do we get a function that gives you back something if you call it? It gives you back different values. It'll be very similar to the one we did up above. Let's try. So I'll call it, I guess I can make a new cell. Why not? I'll call it one bootstrap. We used average already. I'll just call it mean this time. Why not? It's a mean. And we are going to take our births table and we're going to resample from it the same amount of rows with replacement. And that just so happens to be the default because they knew we were going to want to do that a lot. Nice. And so that's our resample. Cool. And what we want to give back is the average of, could have done this in a bunch of different ways. Could have been like births dot column, maternal age dot mean, np dot average, np dot mean, either all three options that I can think of immediately. So we want to do that for the resample now. And so, oops, and give back that value because you always want to return something from a function, of course. And so there is our function. If I call it a few times, we should get back a bunch of different means. This one's a little younger than 27.22. It's hovering around 27 though. And the question is, how much does that vary? Because this is like us pretending to take new samples, right? Take new samples. How much does that vary? And that would give us a nice confidence interval then for like how old the mothers really were in the population. Because this is just one sample. It could have varied. This resampling, this bootstrap process tells us how it might have been different. All right. So the next step is kind of what we were doing before. Let's make a bunch of these values. Let's make a bunch of bootstrapped averages. We can do even more. Let's do 5,000. Why not? give us even more data. So let's generate means from 5,000 bootstrap samples. And so what that's going to look like is we're going to make a, let's set a variable to say how many times we're going to do this, because we can change this. Repetitions, if I can spell repetition, repetitions, 5,000 of them, please. And I would like to make a bunch of bootstrap mean values. Bootstrap means is a blank array. Make me a blank array, please. And I would like to loop for that many times for I in np.arange num repetitions. So that variable just makes it so that it's easy for me to change that if I want to do 1,000, want to do 10,000. And every time I'm within this loop, I want to take a new bootstrap mean value and attach it to the end of this array. Yeah, let's do that. So I'll say np, well, let's do the thing. One bootstrap mean. There's my new value. I want to shove it to the end of this bootstrap means array. So I'll say np dot append to add a thing to the end bootstrap means. Add it to the end. This is the new value. It will give back the value, be replaced with it there. And then remember that np.append does not change your array. It just puts it there. So it just gives you back a brand new array. So to add it in, really, we can replace bootstrap means with this bigger array. And so if we run that, it might take a second, but it's off. And the idea now is once we have this, we can take a confidence interval and we can look at the values and it will be great. All right. So as it's doing that, maybe you try it too, and this can be your next crush dice. Crush dice. I'd like you to try to calculate a 95% confidence interval from the values in this bootstrap means array once it's ready. Calculate, you can at least get the code ready. Calculate a 95% confidence interval. There it goes. It's finished now. Confidence interval for these values using bootstrap means array. Because that's giving all the different ones we were able to generate randomly with these new resamples. And so if we then go and look at the way we calculate a 95% confidence interval scrolling up, is you use percentile, right? You're going to find the 2.5th percentile and the 97.5th percentile, and smack in the middle of that is going to be 95% of all the things we generated, right? And so this is the one right before the line, if you go and look at the code. It's the very last thing that you see in the code that I've given you so far from last time. Try to use that idea to calculate a 95% confidence interval for the average age of the mothers in the population that were sampled. So I guess the mothers who went to this particular hospital, or maybe it was just like a general area. They went around to a couple different hospitals, I forget. But give that a try. It'll look exactly like we were doing last time, but it won't need to be so. How far away from the 27.22 it was? All right. Moment of truth. Let's try it. So it's going to be the percentile function on the bootstrap means array, but I want the 2 point to get 95%. I got to cut it between, right? 2.5 percentile, 2.5 percentile, and 97.5 percentile. So that one, percentile, 2.5 from bootstrap means, and like that's the left edge of my confidence interval, and the right edge, we want to spell it out in a bunch of lines like this, that would be the 97.5th value. And if I want to give back two things at once, of course I can use a comma if I'm lazy, but I can give it back as an array if I want. So there it is. So I can make an array with left and right in them, and that is my confidence interval. And it looks like we can say, assuming this was a random sample and it was taken properly, we are 95% confident that the population of women who maybe went to this hospital and were about to have a baby in the general area where they took this data, they were going to be, on average, aged between a little under 26.9 years old and 27 and a half years old. And so that's what we were able to conclude. It looks like our original average from the sample is probably not too far off from the truth. It's a very tight interval, which is nice. If you take enough data, we had 1,000 things here. That's a lot more than like the 400 that we were playing around with last time. The more data you have, the tighter that confidence interval becomes. I hope that makes sense, because then you've sampled more people, and so you're going to have a better window into the actual ages, which is great. Any questions about this? Does that make enough sense? It's a cool idea, I think. You can go out and get another sample for free. If you do it right the first time, you can do a bunch of bootstrap samples. And so let's look at the graph. We know that the histogram of the ages of the women in the sample look like this. It's a little skewed. It's a little like pinched that way, and I think that means it's skewed right. You're going to pull it that way a little bit. Could also be skewed left. I forget which direction is which. That is not very important to me. But let's take a look at what happens when we did this resampling, this bootstrap means array. Let's look at all the values in it. So let's say, let's make a brand new table with a column called bootstrap sample mean, and that's going to have all the bootstrap means values. So it looks like that. Here's the table. It's got a bunch of these values, of course, and let's call that something. Resampled means, and let's do a histogram of it. Resampled means dot, give me a histogram. You don't have to say column 0 if there's just one column. Just be like, histogram, please. But we can ask for more bins. There they all are. This is kind of interesting and neat. Notice how, this graph is a nice shape that you've probably been reading a lot about, as a bell curve shape, right? We've seen this a lot already. Even though, well, here, let's also plot, before I get ahead of myself, let's also plot on this graph. You don't have to understand what I'm about to do. Let's also plot, though, this confidence interval. So we can see, like, the 95%-ish land is going to be like here and here, or something like that. So the way you do that, apparently, is you say this magical incantation on the plot itself. plt.plot, a rectangle from left to right, negative 0.01, these values on the other axis, 0.01, something like that, and color is some color. They did yellow, and the width of the rectangle is that. That's kind of neat. You don't have to understand that line. I barely understand that line. So this is just plotting as a rectangle. Here's our confidence interval. And you can kind of read it off the histogram as well. It's like this is the 2.5th percentile cut off right there, the 97.5th percentile cut off there. And so it's right in the middle. It's the middle 95% of the bootstrap means that we've generated. That's what it means to be a confidence interval. Okay? That is beautiful, and that's how that works. And notice that this one is a bell curve, even though histogram, like this one above, I'll show it to you here again. Give me this again, please. Give me a histogram of the maternal age. Even though this one's a little skewed, it's a little stretched this way, this one's perfect. Perfectly round, perfect bell curve. That's quite nice. All right? That's interesting. Looks like a bell curve, even though the original distribution, the one below, of the real ages of the sampled women, even though the original distribution doesn't. That's kind of neat. That is the law of averages taking effect, I guess, because we took a bunch of means. That's kind of neat that that's happening. There's some cool math there, but I think that's all that I wanted to say. So yeah, there's that. What else can we say? First of all, are there any questions about anything that we've done so far? You kind of see the process, like, okay, I've got one sample, I'm going to resample it a bunch of times, assuming that was one good sample, like it was taken randomly from the population. I can take a bunch more resamples now and then use that bootstrapping process to generate a confidence interval, because we know that our sample, whatever statistic we take from the sample, is not the true answer for the whole population. We want to see how it could have varied. So that's quite nice. And now I can finally move on to this last bullet here. You can control the percentage. That's what we did. Like you can do 90%, 95%, 99.9%. You can also use it as a p-value, which is kind of neat, because like it's a value. Like I'm 95% confident that the average age of women in this population is between this and this. And you can use that when you're testing hypotheses, because just like a p-value, it's like we're 95% confident that we're right. Bless you. It's like a 5% chance that we're wrong with a p-value of or a p-value of 5% or something. So let me spell that out. Confidence intervals can also be used to test hypotheses, which is a great nice thing. It makes sense. So let's say that we had a hypothesis that like, let's pretend we thought that like, okay, the middle was really here for the women, like before we go out and get our data. Like our null hypothesis is the average. Let's pretend this is true. Let's pretend that our null hypothesis, the thing we're pretending we're not sure is true or not, the average age in the population is 30 years old. All right. The alternative then, alternative hypothesis, would be the average age in the population is not 30 years old. And so we can say now with our confidence interval, let's do a 99% confidence interval. Why not? What would be a 99% confidence interval? You'd go between To test this, we could use a confidence interval. We can be like, we're 99% confident that the true average age is between this and this. So if you want 99%, you start at 0.5 percentile, and then all the way to 99.5 percentile. Does that make sense? Like that's 99 in between. That's a 99% confidence interval. Boop. And it looks like we can say we're 99% confident that the average ages of these women in this population is between 26.8 and 27.7 years old. And so that says that's enough firepower, right? We are 99% confident that's true. That is plenty of firepower to say, no, the null hypothesis is probably wrong. Let's reject it in favor of the alternative. See how you can use that to test something as well, in addition to getting back that range. That's kind of neat. Yeah, I think that's all that I wanted to say about this data set. Are we ready to move on and practice with other data sets? All right, this is going to be mostly on you now, so hopefully you've got all this down. I can move around to other things if you'd like me to. But yeah, now we finally finished those slides. I just want to try a bunch of examples now, let you like have some time to work with it, and we'll see like if the size of the sample is good enough. I haven't tried this yet, so we'll see together. Maybe we need to take a bigger sample, but let's do a Titanic sample. Let's do a size 100 sample of Titanic passengers. I'd like you to try to create first a 95% confidence interval for the average passenger age. Okay? That's what I want us to try, and we'll break it up into steps together, but let's first, I guess. Dun, dun, dun. I guess this is like this is all about confidence intervals. This is within the confidence intervals one. So I'll do 2 number signs. Titanic. Let's bring in our Titanic data set. Step 1. Boop. Oh no, forgot to close the quote. So here's our data set. We've got a bunch of values. We've got about 1,000 rows-ish, 900-ish rows, and we've got ages and survival values. We're going to focus on age first because we were just doing that. That's a good example. So the age column, you got a bunch of them. Some of them, unfortunately, we don't know their age, like this person. We have no clue what their age is, so I think we need to filter that out first. before we do anything else, let's filter that out. Let's do like Titanic dot where the age column values are like above or equal to, just be like 0. And that would get rid of all those nans, which is short for not a number. That's just what you put when you don't have an answer for that. So that would get rid of all of those, and that gives us fewer people, unfortunately, but I think that's going to be what we're going to need here. So that's, let's call that Titanic 2 or something. We'll use that for now, okay? Titanic 2, that's the better table, the one without the nans. So please get that table, and then we'll walk through the process of the sampling, all right? So I think I'd like you to pretend we didn't know about all the Titanic passengers. This is a data set of all of the ones. I think every single one we knew about. Like some of them, like we knew all their names and stuff. Sometimes we didn't know their age or something, and that's why that was undefined. But like this was every passenger, I believe, that at least we know about. So let's pretend we didn't get all those passengers. We were just like we were interviewing the people on the lifeboats or something. Let's try to take a size 100 sample of the Titanic passengers. This one will be without replacement. Let's just be like pretend we went out to them, like the people in the lifeboats, and asked them questions. How old are you? So this one is going to be without replacement. That's us drawing a sample from the population initially. So try to do that, and then we'll, I think the next step is then going to be make a function that takes a resample and gives back the average age of that sample. Okay, so it's going to be very similar. So that's going to be your 2 steps right now. All right, so first of all, let's take a size 100 sample. Let's pretend that's all the people on the Titanic we were able to interview and ask questions about, like a random sample. Size 100 sample without replacement, to pretend like that's all we knew about. And let's see how much we can conclude from that sample about everyone who was on the Titanic. All right, without replacement. Let's pretend that's everybody we knew. And then make a function to generate a resample from that original sample, from your original sample, and give back the average age. So those are the 2 steps. Right now, I'll give you a few minutes to try that, and I'll come around and help if you have any questions. It's going to be very similar to what we did last time with the San Francisco people, like pretending that we didn't have all of them. Like, let's make a smaller sample. Let's do a size 100 sample, and then also try to make a function that gives back a resampled average age. So you can mostly copy and paste what we were doing. I'll give you a few minutes to try that, and we'll go from there. So hopefully you're going to see very quickly, this is all a lot of duplicated stuff. Like you're going to be able to copy and paste a whole lot of what we're doing. It's like the statistic changes. That's the problem. And we'll see how good the size of 100 sample is. Predicting the age of everyone in the Titanic. That's all that we have. We have been really well. Prove to ourselves that bootstrapping is a good idea. Interesting. Just ran into that. Is it working? Oh, perfect timing. All right. Let's see. Let's see. So let's get just one sample. I'll call it sample. There you go. Size 100 sample from Titanic 2, because that one has normal H values now. Titanic 2. Give me a sample of size 100 without replacement. So with replacement equals false, capital false. So there's my sample. And we can look at that. Like, what does our sample look like right now? Only 100. Got all these different ages. Yours is different, of course, than mine because it was random. And now we're going to pretend like that's all that we had. We were able to interview those people on the Titanic maybe before they got on and the disaster happened or something. But let's see what that lets us conclude about the average age of all the passengers on the original Titanic. Like, I haven't checked what the average age is yet. Let's see how good bootstrapping is going to give us values here. So let's make a function that resamples from our original sample and gives back the average age. So, I don't know, one bootstrap average again is going to take us a resample from our sample. Call it, here's my resample equals sample.sample. So just as many this time as with replacement. And then return the average age. So that's going to be return resamples, because it'll have just the same names in these columns. So like, give me the age column, dot column for age, and then give me the mean. That's another way to do it. Something like that. And so that's a function that I can call one bootstrap average a bunch of times. Boop. Boop. Sometimes like it's hovering around 28, 29, 30. Interesting. Oh, that one's 31. So now the question is, all right, what can we conclude about this? What can we conclude about the ages of the people on the whole Titanic? We're pretending we didn't know that, but we can check against the ground truth once we're done with this. But the next step is going to be, let's do, I don't know, do 5,000 of these. I think that's what we did last time, right? Generate 5,000 averages from your bootstrap samples. So let's do that. Generate averages from 5,000 bootstrap samples. Try that. So you're going to make an array that starts out empty, and you're going to 5,000 times generate bootstrap samples. So do that, and if you finish early, the next step, of course, is to then get a confidence interval, and the one we care about for the average passenger age is 95%. Get a 95% confidence interval for the average age. So you can use the array that you've generated then from those 5,000 resamples, bootstrap samples, to say like, all right, the 2.5th percentile, the 97.5th percentile is this and this. Those could be my ranges. And that's going to tell us with 95% confidence how old everyone was on the Titanic on average. What was the average age? Which is really cool. Keep that try both those. There should be a lot of copying and pasting stuff that we just did. More stuff on percentile ranges are from. I'm excited. Let's see. Because it was a smaller sample, that's going to mean that the range we get back is going to be wider, most likely. We're less confident. We can't zoom in as closely. We can't have as tight of a bound because we don't have as much data. The more data you have, the more confident you can be that it's within smaller ranges. Let's see how good a size 100 sample is. Maybe we should have taken a size 200 sample. We will discover. Hmm. That's interesting. Let me know if you have questions as you're trying it. It's going to be a lot of copying and pasting, but it's kind of cool to discover this. Like, I don't know the answer yet. Notice how wide the interval is. And then you can compare it to the original if you want. You have the true data. Another minute or so, and then I'll, as a head start, and then I'll try it too. All right, let us see. Let's see what happens. So I'm going to take 5,000 resamples. Oh man, oh man. So I'm just going to steal all of this code because it's pretty much exactly the same. It still averages, so I can call it bootstrap means all over again. Cool. So there's that. And it's called one bootstrap average now. Oh no. So that's the only difference, honestly. Let it go. And a 95% confidence interval using this thing called bootstrap means again. You could have called it anything. Call it A. As long as you're consistent, would be between here and here. This would be 99%. We can change this real quick, though, to be a 95% confidence interval. So 2.5 to 97.5. Drum roll. Okay. First of all, notice that the interval is wider. For the women, it was like less than a year of age difference, right? Something like that. For the women, for the mothers, our interval, even for here's 95%, it was, yeah, like 0.6 years off from each other. And this was because our sample for the women was about 1,000 of them. It's about 1,000 of them, and so it's harder to get different values when you have so many. All right, they're all gonna go towards one value, which is nice. When you have fewer things, when you have a smaller sample, that means when you take a bootstrap, like you may like take a bunch of big values more often and a bunch of small values more often, and they're gonna weigh down more heavily because it's just like only 100 things. So you have 100 values and you add a giant value to it and you take the average, then the average jumps really, really a lot compared to like if you had 1,000 values and you add a really big value to that, the average is still going to jump up, but not as much, if that makes sense. So that's kind of why we see a wider range here. But yeah, that's what we see from our confidence interval. We're saying that we are 95% confident that the true average age for all the Titanic passengers was between 27 and a half and about 33 years old. Let us see. So we have the true data. We have Titanic 2, right? We have this table. Let's see what the average age is. Give me the column called age. This was the true average age of all the people on the Titanic that we have ages for. What do you know? It's 29.7. So this is again proof, like this is the true value. This is again proof that bootstrapping does well. It's going to confidence intervals work. Okay. Are there any questions about this? That's fun. I like it. So yeah, I want you to try the whole thing now. Do a 99% confidence interval for the survival rate this time. And this one you can go back to the original Titanic table. Go back to original Titanic now. because that one, I believe, the column for survived is always 1 or 0. It's never going to be maybe. So we have some data for that. I don't think it's ever nan there. So like go back to the original Titanic table for that, and your job is construct a 99% confidence interval for the survival rate. And so a way to calculate the survival rate is, because it's 0 for didn't survive, 1 for did survive, you can just take the average. The average. But for a size 100 sample, though. Okay, so take a size 100 sample. Pretend we didn't have all these people on the Titanic. We didn't know. We just we interviewed some of them before they got on the ship or something. 100 of them randomly. So construct a 99% confidence interval for a size 100 sample. You can take it from the original table this time because there was more people in that table. I think survived always has a value rather than age maybe sometimes doesn't. But yeah, that's going to involve take a sample without replacement, right? Here, I'll start a timer while you're working. Take a sample without replacement. Then, okay, that's our sample. That's like this 100 people that we interviewed. And then after that, we'll need what? We've got to find, I guess, a function then to do a bootstrap sample to give me a resample, find the survival rate of that resampled sample, right? And then do that a bunch of times. Do it 5,000 times like you've been doing. Do it 1,000 times. And then the 99% confidence interval will come from the array that you've generated from all those resampled survival rates. You'll take the 0.5th percentile all the way to the 99.5th percentile, because that's 90 in between in the middle there, won't you? So yeah, I think that's the process. Let me know if you want me to scroll to anything. If you didn't quite get something down. I want you to try that. And again, this is us just getting proof that this bootstrap process really does work. Confidence intervals really do the right thing. Because we have the true data. We can compare against the original everybody on the Titanic once we do this. Mm-hmm. First make the sample, then make a function that calculates the survival rate for a resampled sample. Then do that a few thousand times. And then you're ready for your percentile function on the results. Yep.
With or without replacement?
Depends on what you're doing. So to get the first size 100 sample, like you're interviewing randomly 100 Titanic passengers, that one's without replacement because you want to duplicate actual humans. But then when you take your resamples, the bootstrapping process, that one's with replacement, because then things look different. You get different values at that point. Looks like my timer is almost up. I'll give you 1 more minute of a head start. And then I'll work on it.
If the average rate of survival,
Yes.
would you need to get the length of uh, the ones, basically?
If you're going to do that manually, but there's np.average that does all that for you.
Oh.
Or np.mean. That's what we've been using for the average this whole time. It didn't like it.
I thought I would take the length of
The length of the what?
like I have to take the length of the survive column and then do the mean.
No.
Do that, or just like straight up just mean?
Yeah, the whole point of it, what does it mean but add them all up, divide by the size. So like that's packaged into whoever implemented that function for us.
I thought mean was the same thing as average, but I forgot.
It is. Mean is the same as average. Yeah. So yeah, let's try this. Let me get my first sample, like original sample. I'll just call it sample again. That's original Titanic this time. We don't need Titanic 2 anymore. And we want to take a sample of 100 people, please, without replacement. So replacement equals false. We don't want to like clone anybody. It's like these are real people that we're interviewing or something. That's our sample. Let's see what we can conclude from that sample and see how good like of an estimate we can find. So there's my sample, and I would like to then get, I guess I can do this all in one thing. Give me a function that gives me, for that sample, it'll look just like the sample, all the same columns. Give me the survival rate for a resampled version of that sample. That's my bootstrapping process. So I'll call it like 1 bootstrap rate, maybe? That could work. So resample is sample.sample, why not? And then we want the resampled column called survived. And I can say dot mean. You could also have said, it's a bunch of different ways to get the average, right? np.mean, np.average, any of those. Whatever you like. And so if I run that, oh goodness, doesn't exist yet. 1 bootstrap rate. It's like about half, a little under half each time, a little over half that time. Interesting. Let's see what that, let's do that a bunch of times. Let's do it 5,000 times, why not? So we're going to do 5,000 repetitions, why not? Let's call this bootstrap rates, I guess. Bootstrap rates becomes itself plus 1 bootstrap rate. 5,000 times. And then to get a 99% confidence interval, we're going to do a percentile of our B-strap rates. That's the 0.5th percentile, I guess, all the way to the 99.5th percentile. Moment of truth. Drum roll. It looks like we are 99% confident that the survival rate for the people who are on, everybody on the Titanic was between a little under a third all the way to a bit over a half. That's a pretty wide range, and one of the reasons we see such a wide range is because of our sample size. Because we took only 100 things, 100 people, we can't be as confident. So we have to have more uncertainty. The range is wider, which is kind of interesting to think about. Now let's see, like, what for the real Titanic, what is the true survival rate? Survived. Dot mean. Okay, it's about 0.38, almost in the middle of that, which is cool. Cool to think about. So that's the true Titanic survival rate. And also, when you're doing a very large confidence interval, like 99% confident, you are going to have a wider range as well. because like you don't want to mess up. You want to be 99% confident. That means you're going to have a wider range so that you're covering more bases than you would for a 95% confidence interval, right? So that's another reason why it's so wide. But I highly encourage homework, if you want to, try to change the sample size and see how the so like you can just rerun this. Instead of 100, say something else there. Try to change the sample size and see how the width of the interval changes. Because it will. As it will. And so that's a fun example. Again, we've got proof that the bootstrap sampling method is doing the right thing and confidence intervals make enough sense. Cool. Any questions about the Titanic example? Because we got more. We got more. Well, let's do the same thing. Let's see. Yeah, we should have enough time to do both of these. Let's go back to the fish diet one. So again, this was a bunch of Swedish men, I think. Yeah, it's a bunch of Swedish men doing responding. It was Swedish twins actually, which is kind of cool to think about. They were asked how often they ate fish, and like no amounts of fish, small amounts of fish, medium, lots of fish, and then we also tracked whether or not they got prostate cancer. And so let us do the same thing with them. So fish day. And again, I'll give you time to try it. Go slow. Make sure we all understand what's happening, because this is very important stuff. Yeah, so let's read in this first of all. We've got table.read table data slash, is it just fish? Yeah, fish dash diet. We'll call it diet. And so this is not very useful. If I take a sample of that real quick, here are all the different kinds of values. Like you've got moderate amounts of fish. Where's like a never? Show me a never. There we go. Never fish, small fish, moderate fish, large amounts of fish, and like cancer was yes or no, not false or true, not 0 or 1. So that's what we get. That's what we have. And my question now is, let's do the same process. Let's take a size 100 sample and let's do just a 90% confidence interval this time. So it's less confident. 10% chance we're wrong now. It's outside of this range. That's what that means, right? A 90% confidence interval for the total cancer rate among everybody. So you can throw away the diet column if you want to. Okay? So try that, because you're going to have to somehow convert cancer to like yeses or nos. See if you remember how to do that. Or, sorry, the yeses or nos need to be converted to like numbers eventually. Sorry, that's what I meant. Trues and falses. So yeah, that can be your goal. So take a size 100 sample, and then using bootstrapping, construct a 90% confidence interval for the total cancer rate for everybody in the sample. And let's see how close it is to the original cancer rate, which I can show you right now as you're working. So the original cancer rate, oh wait, no, I can't, because I want you to try to remember how to convert this to a rate, because it's not ones or zeros right now, is it? So see if you can figure that out. I will give you a hint in a few minutes. But I'll give you like a 5-minute head start on that. So take a size 100. Pretend again we're interviewing only 100 of these guys. Well, let's do 90% confidence interval. But actually, this itself was a sample, so we'll do something together after this. After we've done this, we're just getting proof that bootstrapping does the right thing. This technically was a sample. This isn't a sample of every Swedish man. Let's see what we can use it. We can do different things. It should be a lot of copying. We just want 90% confidence interval. So it's going to be not as wide as like a 99% confidence interval, but it's not also at the same time going to be not as accurate, potentially. More likely to be wrong. Let me know if I have any questions. I guess my hint to find the rate would be to go back to the last time we used the fish diet dataset. We have options. My other hint would be to use comparisons. Another minute head start, then I'll do it. Alright, that was my timer. I'll try it. Alright, let's do it together. We have, here's my sample. Oh, I'll just call it sample. I've been calling it sample this whole time. Sample.sample is a weird thing to say, so let's call it, I don't know, S. Capital S is my sample. That's diet dot, give me a sample, please. And give me 100 with replacement equals false. There we go. So I've called it S instead of sample this time. I'm gonna make a function that gives me back one bootstrap cancer rate. So we'll call it one bootstrap rate again. And the way to get that rate, oops. So again, we're gonna calculate a resample from S.sample this time. Why not? And then it's gonna be the average cancer rate. But we have yeses and nos right now. We don't have ones and zeros to add up, do we? So the way that we're going to deal with that is we can do a couple things here. Let's calculate the average cancer rate for all these people, for everybody ever. So this is diet. You can ask, hey, was cancer dot column cancer, was that equal to yes? Because that's almost most of the way there, isn't it? You get a bunch of trues and falses at that point. And we know that we can do np.count non-zero, right, to get how many of those were true. We could divide by the size if we wanted to. I'm actually interested in seeing, because np.count non-zero is a way of doing, like, it treats the trues and falses like ones and zeros. Can we just do np.average immediately? Yes, we can. Exciting. So np.average will just work. It will convert trues to ones and falses to zeros. Just like np.count non-zero, just assumes that that's trues are ones and falses are zeros automatically. So np.average will work like that. So that's great for us. We can just like go to column cancer then. Column cancer. Cancer, if I can spell cancer. And then we should be good. And so let's just do it all. 90% confidence interval for, I don't know, 5,000 is fine. More bootstrap rates. Fine. One bootstrap rate. And then a 90% confidence interval would be to take which percentile and which percentile. What are ideas? If I want the middle 90, where do I start? 5, right? And so that kind of forces the other one to be 95. 95, yeah. And that should do it. Oops, what have I done wrong?
I think it's because cancer, you didn't add in the average to it.
Dun, dun, dun. Which line is it unhappy about? Yeah, probably. Example that column cancer. Oh, maybe I did do something weird here. Oh yeah, I didn't do the equal is true. Sorry, equal yes. Thank you. And that was necessary. Yeah. Try again. Thank you. So it looks like, all right, we are 90% confident that the true rate of, wait a second, 0.05. Did I do that? Yeah, 0.05, 0.95, excuse me. There we go. We are 90% confident, excuse me, that the average rate is between 0.01 and yes, 0.01 and 0.29999, so 0.03. Interesting. Did I do that right? Oh no, it was. I did do it right the first time. It was 5 and 95. Sorry. Let me make sure I'm calling percentile correctly. That would be important. There we go, that looks better. That's what I was expecting. All right, we are 90% confident that the rate of cancer was between 4% and 13%. And that just happens to be correct, which is nice, even though it was not the widest. It could have been 10% wrong, right? That's the one. Questions about this? It's kind of nice. The last thing I want to tell you is this was not every Swedish man. This itself, the whole data set was a sample, just like the women who gave birth. So we can do the whole thing all over again. The data set itself was a sample. Let's use it to predict the average cancer rate for all Swedish men, because that was the population it was taken from, right? Let's use the whole thing. The average cancer rate for Swedish men. That's pretty cool that we could do that. This is all over again, except we probably can't do 5,000 anymore. Let's do like 1,000. Probably too many. And it's not s.sample, just sample from diet. Diet.sample, the whole thing. Use the whole thing. Because the data set itself was a sample. And this is going to give us a very, very tight bound, because it was like a few thousand, wasn't it? I don't know how long this is going to take. I probably should have split this up. But it's a diet.sample this time. Now that was the one change, just like use this whole data set now instead. And do you see how when you have a lot of data, and we had what, almost 7,000 people, a little over 6,000 at least, we can say that, all right, we are 90% confident that the cancer rate for Swedish men is, or prostate cancer rate for Swedish men is 6.9%-ish to 8%, 8.0. And that's a tighter range, isn't it? Because we had more data. So not just 100 anymore, it was like 6.2 thousand. So that gives us a tighter range, and this is something that somebody probably wanted as part of this study. This is something that you can generate the confidence interval for just total cancer, which is something important to know. And we can say we're 90% confident that it's between there and there. We could have done, if we wanted a more precise value, we could be like, all right, give me a 95% confidence interval. That would be 2.5 to 97.5 percentiles. And that will naturally produce a wider range because you're covering your bases some more. 95% chance it was within there and there rather than there and there. And usually that's good enough for most statistical purposes. And that's probably what the people who were doing the study, that's one of the things they wanted to know. And that's something that we can generate, which is really cool. Yeah, any questions about that? This itself was a sample. We can use it as such. Cool. So yeah, the last example, we can do it together maybe, is let's do Pokemon. So it's either cereal or Pokemon, and cereal had only like 40 cereals. That was not enough to do this with. So let's do Pokemon because there's like 1,000 of them. So let's do the Pokemon table, and we'll do a confidence interval for those. So let's read that in at least. Table.read table data/Pokemon.csv. Here they all are, and one of the, you could focus on any of these if you wanted to. You can have fun, do it yourself if you know Pokemon. But one of the columns that are useful is the HP column. This is like the number, like how much attack can the Pokemon take? What are their hit points? I think this is at level 50 or something. So some of them are not so powerful. They don't have they can't take a lot of heat when they're level 50. Some of them can more than others. So yeah, that's kind of neat. And let's focus on the HP column. That's all I'm trying to say. So this is, again, a census. This is every Pokemon ever. So there's like 800-ish of them. And I'd like you to try one more time to take a size 100 sample. You can play around, make a size 200 sample if you want. Take a sample of at least 100. Or let's do size 150. I guess that's what I came up with, because that's the number of the original Pokemon. So why not take a size 150 sample this time of Pokemon and do a 95% confidence interval of the median HP rather than average. Just let's do something else. Let's do median this time. And so a way to get the median value, remember when you're trying to generate this for bootstrapping, is you can do the 50th percentile, that's the median, or np.median also exists. Either one. They work slightly differently in that np.median will do the average of the two middle ones if there is no true middle. So for 150, it is actually going to be slightly different which one you use, but it doesn't really matter at the end of the day. So please try that. I'll give you a few minutes. I'll give you like a 3-minute head start, and then I'll just do it. So I feel like we're pretty confident now. But yeah, most of these data sets today, except for like the fish and the women, was about just proving to ourselves that it works, proving to ourselves that the bootstrap process does the right thing when we know the true answer. But if we didn't know the true answer, we can conclude things.
Is this the workshop thing?
Oh, no, this is a class.
Oh,
Are you looking for something?
yeah, maybe I got it wrong.
Yeah, no, you're good. Not here, though. Right. I guess I don't need to say it like that. DY. Oh, that'll be fun. I'm going to stop the timer so that it doesn't go off in my face. There. Let's see. One last time, proving to ourselves that bootstrapping does the right thing. I would like to take a size, I'll just call it sample again. I'm used to it now. Take a size 150 sample of Pokemon. This one is without replacement, because you're just interviewing them. It's like taking a couple, you're not duplicating any of them. With replacement equals false. And then we're going to take a we're going to make a function. That's a good way to do it, right? Make a function that calculates just give me back a median HP for a resampled version of the sample. So one bootstrap, it's median this time, right? And so it's going to give me a resample from my sample with replacement by default. Same number of rows. Sample, good for it. And then we're going to return the median HP value. Return np.median of that resampled samples column called HP. I think it's all lowercase, right? Yeah, lowercase HP column. And then we're off to the races, I think. That should work. And then the rest of this is very, very similar to all of this, which I can copy and paste. We can do 5,000 this time. It's small enough. Do 5,000. It's going to be bootstrap medians this time. Put all this there. It's one bootstrap median. Bootstrap medians, and we want to do a 95% confidence interval, so that's going to be a 2.5th percentile to the 97.5th percentile. And I used too many letters right there. Resample. Start off with an empty array. 5,000 is a decent number. That's fine. And we'll see how this compares to the true median HP value for every Pokemon ever, which we can calculate with the same idea, but just with the Pokemon table. So just proving to ourselves one last time, eventually, that the values are right. So it looks like, all right, the median HP value for Pokemon at level 50, for the we are 95% confident. This is how we say it. We are 95% confident that the median HP value for all Pokemon, because we took a random sample of them, is between 64 and 70. And so let's see if that is true for everybody. It just so happens to be 65. That's the true value. Cool. Maybe with a 90% confidence interval then, because that's kind of small. We might have been a little bit off. I don't know. Unless there were a bunch of 64s duplicated a lot. So yeah, you can try. Eventually, with a small enough confidence interval, you will be wrong more often. Right? 90% confidence interval is not as accurate. It's 10% of the time it's wrong. A 95% confidence interval, 5% of the time it's wrong. But that's why you say it like that. You qualify. We're 90% confident. We are 95% confident that everybody's happy. Okay? So encourage you to play around with the sample size. The num repetitions, as long as you do like at least 1,000, should be decent. That's not as bad as the sample size. The sample size is really what's squeezing the interval or expanding it when the sample is smaller. But yeah, this is just proof firepower that this idea makes sense and works. We can do this bootstrap process. It's going to give us another, if we took the original sample well, and it was a random sample, it was nice, if we resample from it with replacement this time, it will give us effectively new samples from our population, and we can use those to see how our original sample could have varied. And that lets us calculate different values, and we see how often they appear for whatever statistic we care about. And that allows us to generate a confidence interval. You just gotta center it around what we care about and get a number, and we are happy. So yeah, I think that's all that I wanted to say about all this stuff. Are there any questions about the topics? It's a fun idea. I hope you get the hang of it now. You tried it enough. But I think that's all that I wanted to say. The last thing for the day is homework 8 depends on this chapter, so we can schedule homework 8's due date now. And what a luxury. Please do attendance if not. I will stop that. What a luxury for Canvas to be working, because now we can actually look at this together. So let's look at homework 8, and let's look at when things are due. So at least a week from today is when I'll have it be due. What do we got due right now? It appears that, yeah, we have nothing due a week from today, so that seems like a decent due date for me. So yeah, let's do that. That will be the 29th, I believe. Pay no attention to this extra credit one. This is not for this class. So yeah, let's do it. Let's have it due the 29th, and I can do that right now before your eyes. So we'll be doing a week. Dun, dun, dun. At 5, though. Save. And yeah, I think that's all I wanted to say for the day. Are there any questions before I stop the recording?